In this video we're going to take a look at half-life, and to begin with I want us to think about radioactive decay itself. So radioactive decay is a random process, and by that we mean that we can't tell when a specific nuclei is going to decay. A good analogy for this is popcorn. So in this video we've got some popcorn that's being cooked, and here we've got lots of kernels. However, you cannot tell which kernel is going to pop next. You know, there's a likelihood that one will, however you couldn't say exactly which one will be next. Half-life is the time it takes for the number of nuclei of a radioactive isotope in a sample to halve. So here I've got 16 radioactive isotopes. After one half-life, half of those 16 will have decayed, so half of 16 is 8. So if 8 have decayed, you're then left with 8 radioactive isotopes remaining. So after another half-life, half of the 8 remaining radioactive isotopes will halve to make 4, and you will have had 12 altogether that have decayed. Then going from those 4 radioactive isotopes, halving again for another half-life, you're then left with 2 radioactive isotopes and 14 altogether that have decayed to that point. Our popcorn analogy now. If I had 12 kernels, then the half-life would be the time taken for 6 of those kernels to pop, and this would be the same as the time it takes for 3 of the 6 remaining to pop. But if we wanted the time taken to have gone from there being 12 kernels to 3 kernels, that's 2 half-lives. So let's now put some numbers in here. So if our half-life was 30 seconds, the time taken between going from 12 kernels to 6 kernels and 6 kernels to 3 kernels is both 30 seconds. But for going from 12 kernels to 3 kernels, we've got to add them together, and so it would take 60 seconds to go from the 12 kernels to 3 kernels. So a question for us to have a look at: there are 10 million atoms in a sample of radon-222, which has a half-life of 3.8 days. How many undecayed nuclei are left after A, 3.8 days, B, 7.6 days, C, 11.4 days, and D, 1.9 days? Okay, so for the question, we need to consider how many half-lives have happened in each of these periods of time. So our half-life is 3.8 days, and we've started off with 10 million atoms. So A is 3.8 days, and we're asked about how many undecayed nuclei are left. So we're looking at the number of unstable nuclei which are ready to decay. So 3.8 days, this is after one half-life. So 10 million times a half would be 5 million atoms that are undecayed. For B, 7.6 days. This is 2 half-lives. So 10 million times a half and a half again. So that's 2.5 million atoms that are remaining to decay. And C is 11.4 days. So this is 3 half-lives. So 10 million times a half times a half times a half, which is 1.25 million atoms. And then finally D is 1.9 days. Now, without drawing a graph, this one is quite hard for us to actually calculate. So roughly speaking, we've had 10 million here and our decay would look something like this. So this is of course 0.5 half-lives. So we know that at 7.6 days, 3.8 sorry, we will have got to 50 million. So we're looking for an answer between 50 and 10 million, but without doing some complicated maths, which we don't do at GCSE, you can't get an exact answer for this, just a rough estimate. So our rough estimate would probably be around the 7.5 million. However, it would be an answer slightly less than that due to the changing gradient of this curve. So an answer that's less than 7.5 million. Another question to look at, a 10 kilogram sample of cesium-137 has a half-life of 30 years. What is the half-life of a 5 kilogram sample? So this one's actually a trick question, as the half-life of the sample would be the same regardless of how much there is of it. So a 5 kilogram sample would still have a half-life of 30 years, as the half-life is the amount of time it takes for the sample to halve. It's irrespective of what mass you start off with. The radioactive isotope sodium-25 has a half-life of 1 minute. What fraction of it remains after 3 minutes? Is it A, 1/3, B, 1/4, C, 1/6, or D, 1/8? So if we have a half-life of 1 minute, we're after what fraction is remaining after 3 minutes. So after 3 minutes, this is 3 half-lives have passed. So a half times a half times a half, which is 1/2 times 2 is 4, times 2 again is 8. So our answer is D. Half-life can also be defined in terms of activity. So first to remind us what activity is, which is the number of nuclei decaying per second. So this is measured in becquerels, given a symbol of BQ. So as the number of unstable nuclei reduces as they become stable, the activity of the sample must also reduce, as there will be fewer nuclei decaying each second, and therefore your activity, it must be lower. So if we're halving the number of unstable nuclei, then we're going to be halving the activity of the sample. Our half-life therefore can be defined as the time it takes for the activity of a radioactive sample to halve. So a question to have a look at, a sample of cobalt-60 has an activity of 2000 becquerels. What will the activity be after 10 years, given that cobalt-60 has a half-life of 5 years? So a sample of cobalt-60 has an activity of 2000 becquerels. What will the activity be after 10 years? So this is at 0 years. And it has a half-life of 5 years. So we're talking about going 2 half-lives. So 2000 times a half and half again, which is 500 becquerels. Another question, a sample of strontium-90 has an activity of 5000 becquerels. After 120 years, the activity has fallen to 625 becquerels. What is the half-life of strontium-90? So a sample of strontium-90, our activity at 0 years is 5000 becquerels, and then at 120 years we're at 625 becquerels. So we need to know how many half-lives it's taken to go from 5,000 to 625. So one half-life would be 2,500, next one 1,250, and then 625. So that's 3 half-lives. So 3 half-lives is that 120 years. So then one half-life, or the half-life, is going to be 120 divided by 3, which is 40 years. Is how we use graphs in order to work out the half-life. So here we've got a graph of number of radioactive nuclei on our y-axis and our time in hours on our x-axis. So we can use this graph to find the half-life by looking at the time it takes in order for our number of radioactive nuclei to halve. So we can pick a point, so 1,000 nuclei, which there are at 0 hours, and then where 500 nuclei would be, as that's half of our initial amount, and then look at the time it takes to go from 1,000 to 500. And here it's nice and straightforward, 7 hours would be our half-life. If I look at this graph, and again take 1,000 and 500, and see the points at which they cross, we could also, here as we've got more data, go and do our next half-life, so half of 500 to 250, and what we should see is that the time taken there is the same going from 1,000 to 500 as it is going from 500 to 250, and so by calculating the difference we can work out the half-life. Going to recap the half-life question from your atoms exam questions from many weeks ago now, but just to go through how you calculate half-lives using a graph, using an exam style question. Use the graph to calculate the half-life of gold 198. So our half-life is the time taken for half the sample to decay, or time for the activity to halve. Both happen at the same time, because if you're halving the amount there's going to be less decaying, and so therefore your activity would also have halved. But it just depends on what your y-axis is as to which definition we're working with. So here we're looking at a count rate, and so we're looking at our activity. So if it's starting at 600, our half-life is going to be the time it takes for it to get to 300, which is here. And that looks 2.7 days. So here they've asked you to show on the graph. So I would be using a ruler. Make sure you're drawing your lines down and along, showing that clear half from 600 to 0, but you could have picked any other point and halved it. So for example, 500 is here, and then you want to go to where 250 is, which is here, and that distance should be the same, as the half-life is constant. So our distance from here to here should be the same as the distance from there to there. If you took 400 here to 200, which is here, again that distance should still be the 2.7 days. doesn't matter where you start, so long as you're halving your activity and reading off the points of the graph and then looking at the difference between them. I always find it easiest choosing my first one as the 0, because it then just means I can just read off my x-axis as to what the half-life is, but you could choose any of these points, halve it, so long as you've still got a corresponding point on the graph to match it up to.